next speaker is Margarita Boyarskaya, who will be talking about full characterization of adaptively strong majority voting in crowdsourcing.
Hi everyone, excited to talk to you about this. Okay, let's go. So we're talking primarily about settings where labels provided by human annotators are indispensable. This applies to various settings where you want to have very tight control on the accuracy, labeling undesirable LLM outputs is just one example. Citizen science projects where there's no machine learning solution for labeling data is readily available, or higher stakes arbitration of cases that were initially flagged by machines that need to go through human review, and we need human labels. So typical way that we aggregate labels, you can think without loss of generality about like binary classification for now, typically require majority voting, some version of majority voting to control for the fact that humans give noisy responses. Moreover, on top of that, different workers, we will refer to them as workers, kind of paying homage to the crowdsourcing platforms convention, they have different accuracy levels. So how do we structure a crowdsourced voting process to achieve some desirable target level of accuracy? That's the motivating question. What is the cost of running such a process? And ultimately, can a pool of lower accuracy workers achieve the same accuracy as you're getting by hiring better accuracy workers? And if so, what is the way to remunerate these two groups relative to one another? So more of the lower skill versus fewer of the higher skill. And how to deal with uncertainty in the worker accuracy to begin with. So we provide closed form theoretical formulations that quantify ex ante, a priori, the expected quality and cost of the consensus labels when you are using a particular consensus scheme that is quite common. We show that we only need some prior knowledge of the prior expectation of the accuracy P to estimate the process quality and speed in real time as the label occurs. So as you're getting more votes, you're getting more information about what is the accuracy level of the workers that you do. So a little more concretely, think about binary classification of a single item. And what you're doing is you're soliciting votes from workers, from humans, sequentially. And each worker has an unobserved accuracy P that means that they provide a correct label or vote with probability P, and it's drawn from a distribution. The distribution is unknown to you, but you assume that the mean of it can be described as some kind of like stable PI. So although different items can have different accuracy levels, this is the assumption that you're making. And now, how do you define a majority? It's a stronger, also known as adaptive version of majority voting. You call something a consensus when the number of votes for one class outweighs the number of votes for the other class by a fixed threshold delta. So I'm going to keep collecting votes until votes yes dominate over no by delta. Okay, so it turns out that this very traditional, well-known, well-studied model from probability theory is perfect for describing this type of majority voting scheme. So Gambler's Ruin is a process, which is a random walk, where your current state in this chain is signifying the difference between current numbers of correct and incorrect votes. This is us applying Gambler's Ruin to this type of delta majority voting procedure. And so you're starting from 0, and if you collected one correct vote, the difference currently is 1. And then if you collect another correct vote, it's 2, and so on. And these are the observing states. So if you reach either delta or negative delta, observing state, you've corrected the consensus vote. It may or may not be correct. Okay, so yes, we utilize established results in Markov chain theory to characterize the following aspects of this whole process that you can use on real crowdsourcing platforms and people do. So the quality of the resulting labels obtained from the voting process. So what's the probability that the consensus vote is going to be correct? Expected number of votes necessary to reach a consensus. So when will this process terminate? Variance of that number, also the probability density. So we begin by assuming first that the mean P of the distribution of worker response accuracies for a fixed item is known. A strong assumption, but we're going to relax it. So first result that we have is that this formula here, where P is the odds, so ratio of probability of giving correct response divided by the inverse of it, is describing the probability that the consensus vote is correct. So now you can design your crowdsourcing voting procedure with this result in mind to a priori try and get a handle on how good your results are going to be, but of course conditional on you knowing what P is. We're going to talk about how to relax that. So let's put this in context. The parameter delta, so the strictness of your majority rule, plays a significant role in the quality of the consensus vote. So consider workers that on average respond with accuracy 0.75. So if you set delta, so your requirement for how many votes more for one class over the other you want to be equal to 2, then the expected quality of the results is 0.9. And if you increase that delta, so you want a stronger agreement, then the expected quality is 0.96, and so on. So, is this process guaranteed to terminate? How many votes do we expect to collect until reaching a consensus? We want to estimate the number of votes it takes to reach state delta or negative delta in terms of transitions in the Markov chain. You can refer to the paper for the details of this, but this is the ultimate result, which is also important. So this, why estimating the expected number of votes you need is crucial in practice is because this is a proxy for your costs. This is how many people you would need to hire or how many times you would need to make a payout to a worker who is giving you the link. So quite important. Visualization of the formula that you're seeing. So when the odds get close to 1, the expected time to termination peaks at delta squared. Expectation is useful, but we would also like to know how robust the process is. How reliably will the voting finish within the expected time? So it is important to know the variance of the number of votes you need to collect in terms of the number, so as well as the PDF. Variance formula is right here. This odd notation stands for a particular kind of coefficients that I give a few examples of right here. So yeah, this is the ziggurat. So presented results do assume that the mean labeling quality is exogenously known, and that's a strong assumption. So by default, you're hiring some people on the platform. Not only are their accuracies non-uniform, but you also just don't know who they are. Typically, this is handled just ad hoc. So you start a voting process, you see how good the results are, you kind of figure it out as you go. We can do better than that using this theoretical formulation. So we can relax this assumption of known P by modeling the mean worker pool accuracy as a random variable. So if P is average accuracy when labeling a single item, we can assume it to be constant for a single item, but its exact value might be unknown. So we will have a prior expectation about P, and based on the votes that we solicit as we go, we're going to update the values. So we're working first with a simple beta prior for A. We drop the assumption of known P. Instead, P is a random variable. We learn it using Bayesian estimation during voting. So the conjugate prior is beta, which is helpful. So then everything you kind of get for free. The likelihood of collecting N1 positive and N2 negative votes, which is what you're observing as you go, is then distributed as beta with the following change to the initial parameters. And we usually use symmetric priors because a priori you kind of don't know much about your mixture of voters. So you can use all of the previous results, so all of the formulas we have for quality of the consensus vote, expected number of votes, variance thereof, in a similar fashion, straight up. This is the result for the quality. And similarly, we can rewrite all others. Okay, so here are the Monte Carlo estimates of the expected quality of the consensus vote and number of steps to completion. And the interesting thing here is that probability of labeling an item correctly will be different for different combinations of outcomes as the votes keep coming in. So for example, if your delta, so the parameter for how much dominance you want to call something a consensus, is equal to 2, then a process that terminates with a combination 2 positive votes, 0 negative votes will have a different estimate than a process that terminates with 3 and 1, both of them reaching that threshold, and different from 5 and 7. So So this intuitively makes more sense than the results we would have obtained had we assumed a fixed P, fixed worker accuracy. I will just breeze through how we further extend this to working with a mixture of priors. So beta is often insufficient to express our prior knowledge about worker accuracy. In reality, you may be motivated to think that workers come from a mixture. You have some of them that are very accurate, some of them that are less accurate. And so the procedure is then as follows. We jointly update both the parameters of the individual beta distributions and the mixture weights. Okay, now let's switch gears. One of the questions that motivated this whole inquiry, if I pay some kind of wage to workers whose accuracy is P1, how much should I be paying to a pool of workers whose accuracy is twice that? Conditional on the fact that I have a fixed budget and that I expect to get the same quality. I might need to hire more of type 2 workers versus type 1, but how do I set the relative payment? Think about binary classification again. So the goal is to achieve that quality level Q of the resulting labels. If the quality is fixed, then perhaps I would need more demanding decision rules for lower accuracy workers. I want to be stricter while having them adjudicate the test. And then a fixed reward for a given quality means that more workers are required potentially to attain the same quality. And how should we adjust the pay? So you have two sets of workers, accuracy levels P1 and P2. The first set of workers, you are having them, run the delta margin process with threshold delta 1. And then the question is, what should I set the threshold for my stronger majority rule? What should I set the second threshold, delta 2, for that other pool of workers so that I can get the same quality? And this is the answer. And from here naturally follows also a way to tie this to costs. So if you want your expenditure to be the same, your budget is the same, and you know how many more people you would need, and then you might want to pay teams of workers with different accuracies in a way that is fair in this narrow sense of fairness. So the idea is increase the threshold for consensus to compensate. However, that would increase the expected number of votes, and your budget is the same, so you're going to pay them less. And this is the ratio of payments that we propose that comes out of the theoretical results we presented earlier. Okay, so again, if you don't know the exact accuracy of the workers but have prior expectations, follow the same pattern that I described before. Happy to talk about this offline. Trying to usher this along. Okay. Yeah, so this is a heat map that is useful for comparative purposes. It's kind of a measure of equivalence of payments. So consider a scenario where you have delta equals to 3, that's the consensus threshold, and a voting result of 3 yes votes, 0 no votes. The payment level that corresponds to this is 1.1. Units don't matter. Alternatively, if another pool adjudicates the same item with higher delta and a result of 5.1, and that was the terminal vote, then the payment per vote decreases to 0.64. And it sounds like I'm done, and thank you all very much.